Welcome to Digital and FinTech Analytics channel.
Okay, now let's learn the concept of temporal ripple effect with the help of this code. So there are a lot of print statement in this function which is not required, but for the sake of explanation I've kept it. Let's understand this code with the help of the output of this code first, then we'll get into this code. So so say like in our uh, data frame we have like this user ID 1 who has like this list of transactions that has been done in the historical basket. So basically in the past transactions, the user ID one has done all these transactions in the past. So so like will pass this list of, so for each of the users we have those list of transactions. So we'll pass the list of transactions done by user ID 1 to this function, which helps in completing the temporal ripple effect. Uh, uh, so, so this function is known as decay weight assigning, and we are passing all the list of products uh, that the user ID 1, which is corresponding to the index 0, has been passed, and along with that we are also passing the total number of items that is present in the database. So if you remember earlier, I had shown the total number of prior products or like total items in the database is around 11,997. So we are passing that too. So what's happening over here? So first thing we see over here is like these are the transactions that has been done by user ID 1. So how many transactions are these? These are total of 13 transaction has been done. And total number of items that we have passed to this function decade weight assigning is around 11,997, which is coming from this item number variable. So what's happening over here is like we have total of 13 transactions, and the most recent transaction being the first transaction and the most earliest transaction being the 13th transaction. So so like what this function does is it will start from 12th transaction being the most earliest transaction, and it will assign uh, a weight decay value of 0.9 to the power 12. So zero point 0.9 to the power 12 is because this is the 12th index, and this is present in the 0th index. So this is the 12th index transactions, this is the 0th index transactions, and so on and so forth. This is the first transaction, or like the first index transaction. This is the second index transactions. This is the third index transactions. It's a list of list. So what it does basically is in the corresponding to this 13th transaction, it will create a vector which is of length 11,997, and each index of this vector of length 11,997 represents a distinct product ID. So out of those 11,997 products, it will assign the index value 0, 1, and 2, the weight decay values of zero point 0.9 to the power 12, which is basically 0.2824. So this 0.2824 will be assigned to the index value of 0, 1, and 2. So 0, 1, and 2 index value over here represent item number 0, item number 1, item number 2. Similarly, when it will be in this particular transaction, which is basically our 11th transactions, so so what it will do is like it will again create another list which is of length 11,997, and corresponding to the index value of third, fourth, fifth, sixth, seventh, or in other words, corresponding to the item number third, fourth, fifth, sixth, and seventh, which has been purchased in this particular transaction, we will assign a weight decay value of zero point 0.9 to the power 11, since this is the 11th transaction. And similarly, for 10th transaction, we'll be assigning zero point 0.9 to the power 10, which is basically 34867 to the item number 8th, or like the index position of 8th, and so on and so forth. We'll do it until the very recent transaction, which is the 0th transaction. If you see in the 0th transaction or the most recent transaction, user ID 1 has purchased item number 48, 49, and 9. So if I scroll down a little bit, yeah, we see, so the user ID 1 has purchased item number 9, 48, and 49 in the most recent transaction. So what we do in the most recent transaction is like corresponding the recent transactions or the 0th transaction, a vector is created which whose length is 11,997, and in the position of ninth, 48, and 49, or like in the index value of ninth, 48, and 49, or the item ID 9, 48, and 49, we'll be inserting the values of weight decay value of zero point 0.9 to the power 0, which is basically 1. Anything raised to the power 0 is 1. So that value will be inserted to the index position of ninth, 48, and 49. So we can see, since there were a total of 13 transactions, so a vector of vector is being created. The length of the total vector is like 13, because there are like 13 transactions. So corresponding to each transactions, there is a vector which has been encapsulated outside with the help of another vector, and the length of each vector, or the length of each list, is 11,997. And the final vector that will be returning is like this history list that I was talking about. It will be having, it will be of total length 13, because we have 13 transactions, and corresponding to each transaction we'll be having a list which is of length 11,997. Okay, so these are like very sparse vectors, so you see like most of the values being 0, but if you look into each of these values, you will find like there are certain non-zero values in it, which has been shown over here. So if you see like in the very first transaction, we have in index number 0, 1, and 2 non-zero values, and it has 0.2824 is zero point 0.9 to the power 12 is present over there in like the index number 0, 1, and 2, which we can see because it's the beginning index. But when it comes to the next transaction, which has item number third, fourth, fifth, sixth, seventh being purchased, so corresponding to those element only, we will be having the weight decay value 0.313, 0.313, corresponding to all these elements, and that is also present over here, but it is not being shown over here due to the length being too large for this list. So now let's get into the code and understand it, how the code works. So yeah, so first thing what we'll do is like we will create an overall list. Then uh, we'll be creating some intermediate list. We'll see like the use of this list later on. The first thing that we do is like we print the products that are present corresponding to user ID 1 that has been passed as a parameter. Corresponding to user ID 1, whatever the historical transaction has been done, that is being printed over here, and it has been passed as a parameter, and the total number of items that we have in the database is also being printed over here. So we'll see the output corresponding to this line of code. So over here we can see like product as per transaction order. So user ID 1 has purchased all these items, and these are the transactions, this being the most earliest transaction, and this one being the most recent transaction, and the total number of items in our database is 11,997. Next, what we are doing is like we are keeping a decay rate value as 0 0.9, and num numvec is basically the total length of the transaction that has been done by this user. So the total number of transactions that has been done is what we can see. The total number of transaction done is 13. So total 13 transaction has been done by this user. Now what we are doing is we will be looping over each of the transactions starting from this one, 0, 1, and 2. So it first of all, so we see like it's a list of list, right? So when we are looping over this product as per transaction order list, then in the first iteration it will take these transactions into account, then in the next iteration it will take this transaction, and so on and so forth. So let's see how it does. So in the first transaction it picks up like the 0, 1 and 2. um, so in the first transaction it picks up this vector, and it saves the uh, it saves the value of this index, or like this product IDs in item index, using this indexing command. And what it does is like it will create a vector of length, um, and then what it does is like it creates a vector of length 11,997, but the whole of the vector is a zero vector, so all the item in that vector are zeros only. So that's how we do it using np.zeros. So it's not a vector anymore, it is known as an array, numpy array. So it creates a numpy array of length 11,997, and all the elements of that array is 0. Now what it does is like the purpose of creating this array is, once that array is ready, it will insert few weight decay values in the index position of 0, 1 and 2. That we will see how is it being done in the next couple of steps. So first it what it does is like it checks like how old the transaction or the index is. So basically how old the transaction is means like this is the most earliest transaction and this is the most recent transaction. So if we count from here, this being the most zeroth transaction, this will be the 12th transaction. Okay. So so on the basis of that, it calculates like numvec minus 1 minus index. Numvec over here is basically 13, minus 1 is basically 12, index value is 0. So how old the transaction is 12, and the weight decay values assigned is, because according to the position of this transaction in the transaction history, the weight decay values are assigned. So for the 12th transaction, the weight decay value is like 0.9 to the power 12 is what we'll be calculating. So that zero point 0.9 to the power 12 is being calculated and saved in like this variable decayed val. And then what we do is like this vector we created of length 11,997, which has all zeros in it. So corresponding to the index value of 0, 1 and 2 that we are getting it from here, we will be inserting this decayed value of 0.9 to the power 12, which is basically 0.284, 2824. So you see right over here, using this line of code, we are inserting 0.2824 to the index position of 0, 1 and 2, because this is the 12th transaction. So 0.9 to the power 12 or 0.2824 is being inserted to that particular position. Next we are next in the next particular step, here is vec dot non-zero. We just want to do a QC to know like which indices have non-zero element in this particular vector of length 11,997. And using this particular command, we will be looking into what value is present in those non-zero element index. This one we just inserted, we just need to check what value is present. So that is being done over here. We are printing like the historical vector of like the non-zero elements and the non-zero indices. So if you see this particular line being printed over here, yeah, so we can see like that particular line being printed over here. So we see like the his in the his vec we see um, which is basically the non-zero elements. So we see like the value of 0.2824 is being inserted in the non-zero elements, and in which index are these values being inserted is basically in the index value of 0, 1, 2, corresponding to item IDs 0, 1 and 2. Similarly, this is a for loop which will be looping over all the transactions. So in the next transaction, let me explain it with the help of the next transaction. The next transaction is basically the transactions where like the user has purchased item number 3, 4, 5, 6, 7. So this is basically the 11th transaction, and for this transaction also, like the a vector is created of length 11,997, and corresponding to the index values of third, fourth, fifth, sixth, seventh, weight decay value of zero point 0.9 to the power 11 or 0.31 will be inserted to the to this indices. Or in other word, what happens over here is like, first of all, for 11th transaction, a vector, empty vector is being created which has all zeros, and the length of that vector is 11,997 that we just saw over here. Okay, and then corresponding to this index values, or like this item IDs, third, fourth, fifth, sixth, seventh. So as I was mentioning earlier, the length of the vector is 11,997, and each position of the vector, or like each index of the vector, represents the item numbers. So here item number third, fourth, fifth, sixth, seventh will be given the value of zero point 0.9 to the power 11 or like 0.3138, and the rest of the vectors will be 0. So we will do that same thing for all the transactions until the most recent transaction, which is our transaction transaction index 0, and 0 the most recent transaction will be having the highest weightage. So we see like the items that have been purchased in the most recent transaction, which is item number 9, 48 and 49, have been given the values of 1. um, and the final vector that we are returning is like this history list, which is a vector of vector, and we can see like it's a vector of vector, and it is of length 13 because 13 transaction has been done, and corresponding to each transaction, a list is, or a vector is created, or a numpy array is created, and the length of the numpy array is like 11,997, and corresponding to the items that have been purchased in each of this transaction, a weight decay value is assigned, and the rest of the uh, vector is 0. So you can see like it's mostly a sparse vector, and we can see an overall view of like what is the total length of the his list that is being written, and what is the length of each values in the list, or like what is the length of each transaction. So here the length of each transaction is 11,997, and out of which like the transaction that has been and out of which the items that has been purchased in each of the transaction has been marked with a weight decay value, is that can be seen over here. And the same process repeats until the most recent transaction. So the items purchased in the most recent transaction will be given the weight values of 1, since it has like more weightage. So just a recap, what we did previously is like we took the historical transactions of 100 of the training users and 100 of the validation users, and saved it in respective data frame dfhist and dffut. Now what we did is like we understood the decade weight assigning function which executes the temporal ripple effect with the help of a single user ID. So we saw like how by passing the historical transaction of a single user ID, we see like those transactions are being converted into a embedding vector. Each of the transactions of the users are being converted into an embedding vector. Now we have to apply the temporal ripple effect for all the training users as well as the validation users for whom like we created this respective data frames. So dfhist and dffut would look something like this. So for in dfhist we had like for all the training users, basically for 100 of the training users, we have their transactions history, Uh, Now we have to convert each of the transactions into their corresponding embedding vectors that we saw in the previous example. So for that, what we do is like we call these functions, which is like decayed weight assigning. I have removed all the print statements because those were like just for explanation purpose and is redundant while we are running it for all the users. So how we call this function is basically we write like dfist.apply, and this functions inputs like two parameters. One is like the transactions history as well as the total number of items in the database. So we are passing both of these over here. What we are doing is like we are uh, applying a function decade weight assigning, for which we used to write dfis.apply lambda x is to decade weight assigning, and we pass like two parameters over here. One is like the transaction history and the item numbers, total number of items, that is total number of items in the database. And this function will execute with the required information and will return us like two different and will return us two output. One is like the embedding list of list and the total number of transactions. So to get those two transactions in two different columns, which is like within decay rate list as well as like the length, we have to pass another parameter to this pandas apply function, which is like result type equal to expand. So what it will do is like it will expand these two lists such that it will each of the list goes to the respective column. So his list will go to like within decay rate list, and length of his list will go to the length column. And we can see the final output after we apply decayed weight assigning function to dfhist and dffut, and we see like for each of the user id, these were like the historical transactions. So total of 13 transactions were being made for user ID 1 that we saw in the example before, and their corresponding embedding vector. So each of the 13 transactions have been converted to the embedding vector. So 13 vectors corresponding to each of the transactions, and the length of the vector is like 11,097 that we saw, which is equal to like the total number of products, 11,997. So that's pretty much on how temporal ripple effect works. We will see the whole picture when we will club temporal ripple effect with temporal fractures in the next couple of sessions. Thank you.
That's a wrap for today's video. If you found this content valuable, make sure to hit that like button and subscribe to the channel so you don't miss out on future insights into data science, AI, machine learning, and analytics. Looking to master data science or drive data-driven success? I offer expert training, mentorship, and consultancy for individuals and organizations. Let's collaborate. Reach out via my contact details in the bio.